All right, Math 6610, more on central limit theorem. To follow up this central limit theorem and give you another application, pretty similar. The previous video, let me get my bearings straight. This is kind of a hard transition to make. The previous video focused on a distribution that was defined by its population mean and standard deviation. And I just refer to these, because I'm not that creative, as means. But we also deal a lot with proportions. And essentially, what we have in this case is quantitative data. And in this case, we have categorical or qualitative data. Now, for example, let's think about we can have an average ACT, an average GPA, an average house price. But what if we get into like the percentage of something in our population that's defined? Just for example, kind of a goofy. Something I ran into the other day, because I'm a nerd at this stuff, is 30% of people, there was at least a claim that 30% of people believe in ghosts. Well, you have to think that this is categorical because it's either coded as 0 and 1, do not believe in ghosts, or do believe in ghosts. So these are really, we usually code zeros and ones, but they're not quantitative because the zeros and ones just hold a placeholder for the no's and yeses respectively. So in this illustration, then 30%, so if we have 100, there would be 30 yeses and 70 no's. So these type of distributions can also be modeled by the central limit theorem with a small caveat. So again, the process is the same. We start with a population where instead of mu and sigma being known, the percentage of the population is known. Now the conditions here are a little different. We have n times p and n times 1 minus p both need to be greater than 10. Now again, our n is going to be our sample size, which in the previous example had to be greater than 30 if we had a non-normal distribution, or just 2 or larger if we had a normal distribution. So that's the same n. It's the n that we use to sample from this population. And our p is just that value right there. In this case, it would be equal to 30. So if both of these are true, again, huge if both of these are greater than or equal to 10. And I will tell you that some people claim that as long as it's greater than 5, I take a little bit more conservative measure here and set 10 as the threshold instead of 5. So anyway, if all this is satisfied, we would first of all set n, and I'm just going to say that n is going to be 200. Now let's just use this 0.30 claim here. So is 200 times 0.3 bigger than 10? Well, obviously it is. It's 60. And is n 200 times 1 minus p, which in this case would be 0.70. So that would be what, 140? Well, clearly bigger than 10. So the conditions for the central limit theorem are set. So here's what happens. We dive into our population. We pull out 200 people and ask them, do you believe in ghosts? This will be our sample proportion number 1. Notice that the notation for a sample proportion is p hat, and I put a 1 there because it's my first sample, versus p, which is the population proportion. Throw these 200 back in the mix, randomly sample 200 again, find the proportion that believe in ghosts of only the 200. Do this again, do this again, do this forever. All right, now what do we have? We have a whole bunch of numbers here, probably somewhere around 0.3, maybe 0.27, maybe 0.42, maybe 0.28, maybe 0.5, you know, who knows. But there's all the options of pulling out 200 at a time from this population with p 30% of the sample proportions. Well, it should be sorry, I'm not talented enough to write and speak. It should be no surprise to you that these are called the distribution of sample proportions, p hat. Now, what's the central limit theorem tell us? Well, this central limit theorem tells us that these p hats again, forever, I'm going to write this out because I understand that people skip around. So the distribution of sample proportions p hat will first of all be normally distributed. Now that's a good thing, right? It's a good thing because that tells me that in R I can use my p-norm calculator. I can't use my p-norm calculator if I have a distribution that's not normally distributed. So the central limit theorem tells me that I have a normal distribution, which again is a good thing for me because I can use the p-norm calculator. The second thing, again, normal distribution is defined by two things, right? It's defined by its center, it's defined by its spread. Now, let me demonstrate that. In case it's been a while since you've taken an undergraduate stats course, if I have a range here from 0 to 100, and let's say I have a mean of 30 and a standard deviation equal to 5. What does that tell me? That tells me that out here at 30 is going to serve as the center of the distribution. And if I go 5 units to the right and 5 units to the left, this will serve as the inflection part of the normal distribution. Now, how does that contrast with, say, a mean of 50 and a standard deviation of 25? Well, in this case, my mean would be 50, so that tells me that my distribution is going to be centered there. Have to come all the way down to 25, kind of convenient, go all the way up to 75. So that tells me that my inflection part, notice how I have a lot more variance, so my distribution is going to be spread out more, okay? So again, the mean defines the center, the standard deviation defines the spread. Every normal distribution is defined by these two quantities. So this tells me that, or the central limit theorem tells me that the mean of these p hats will be equal to p that we started with in the beginning, and the standard deviation of these p hats will be p times 1 minus p over n. And again, this is called the standard error. So 30% of people believe in ghosts. A random sample of 700 people is collected. What is the probability? That less than 28% of the sample believe in ghosts. So we know that the distribution of all sample proportions in this case will be centered at 0.30. We know that the standard deviation or the standard error will be equal to 0.30 times 0.70. And I forgot what my sample size was. 700. So this spread right here will be defined by this quantity. Now, in terms of we want less than 28%. So if we can find that area, we've easily got the answer to our problem. Well, with R, we can easily do that. So P norm, since we need below, so 0.28. The mean is 0.30. And we need 0.3 times 0.7 divided by 700. So the probability of getting at most 28% is about 0.12. Now, the next trick to the puzzle is to make the connection between what we've learned about the central limit theorem and inference, and I will do that in future videos. All right, take care.